Welcome to analyzing quadratic functions for Pre-Calculus Math 11, and today we're taking a look at the properties of a quadratic function, which is section 4.1. A quadratic function is a function that really can just be written in the form y equals ax squared plus bx plus c. And basically the a, b, and c have to be real numbers, and a can't equal 0. This is called the general form of the equation. So it's just a very general form of this function. We don't really get too much information, and when we graph this, the graph of a quadratic function is called a parabola. So last unit we saw a lot of stuff about how a quadratic relates to its zeros, how we solve them. Now we're taking a look at their graphs. So what do we do when we want to graph a function? Is, you know what, a table of values is usually the best way to go about this. So I'm going to throw down some options here for the x value. -4, -3, -2, all the way up to, we'll go to 3, I guess. Picking those numbers mostly because I know what values are going to work out reasonably well, but even on any kind of table of values, you're always going to pick numbers around 0 probably. And just to show you off to the side here, a quick value, y equals -4 squared plus 2 times -4 minus 3. That would be 16 minus 8 minus 3. And 16 minus 8 is 8, minus 3 is 5. So at -4 we get a value of 5. So I'm going to go through this, calculating these very quickly. -3 has a y coordinate of 0 when you plug it in. -2 has a coordinate of -3, -6, -3 again, 0, 5, and 12. So let's plot these points. I kind of have the grid already skewed a little bit to the right a bit. -4, 5, so 1, 2, 3, 4. Let's assume that's -4 right there. Draw a nice dot there at -4, 5, assuming that's 5. I'm not really going to label off terribly many of the hash marks, but just to show you, there's -4, 5. -3, 0 is certainly a point of our graph. -2, -3, -1, -6, so -6, 1, 2, 3, 4, 5, 3, 6. There we go. And we have 0, -3, 1, 0, 2, 5, and 3, 12, which doesn't really fit on our curve. So we need to try and connect the dots here with a reasonably smooth curve. So coming in fairly steeply here, and if I could curve it off a little bit, I'm sure it would at the bottom, but it's a little bit too fine right now. And let's put arrows on the end of those because we know that that continues on forever, and we've seen that 312 clearly is a point on that curve. So there's a couple of points of terminology that we need to talk about here. The vertex, first of all, the vertex is basically the maximum or minimum point on the graph, and it's written as a coordinate point. So right now the vertex is this coordinate right there. We have a vertex, I'm going to use V for that, and we saw already that that is at -1, -6, so as an ordered pair. The equation of the axis of symmetry. The equation of the axis of symmetry. The axis of symmetry is an imaginary line which cuts our graph perfectly in half, so it's balanced nicely on the left and on the right. It's a vertical line, as you can see in red there. So that vertical line is of the form x equals, because vertical lines that have always the same x value, whereas the y value changes, and it looks like it's -1. And we can see that it's always the x coordinate of the vertex. The y-intercepts, so this is the point where the graph crosses the y-axis. We can see that in this region right here. We have a y-intercept of negative 3. X-intercepts, 2 of them in this case, and you have the potential of having no x-intercepts, 1 x-intercept, or 2 x-intercepts when we talk about parabolas. So here I can just pick off from the graph, that's at negative 3 and 1. Domain, so domain, that is the values of x where the function is defined. Now for a parabola opening up and down, the domain as x is such that x, and we're going to use a fancy e there, is a member of the set R, which is all real numbers. So any value of x is okay. Because really, when we pick any value of x and plug it into the function, it works. There's no restrictions. Finally, the range here. The range actually has to do with y here, given that, and in this case, the range has to do with the location of the vertex. So we have a vertex at negative 1, negative 6. So it's all the y values which are greater than or equal to negative 6. So there's the range. So we have a couple of pieces of information. We have graphing by a table of values. What I'd like to see you do is hit pause and try that exact same thing. Maybe what I'll do here is I'll write down some values that you might want to explore. Negative 2, negative 1, 0, up to, let's say, 6. Seems like a lot, but there's a lot of good points in there. So why don't you hit pause now and see if you can graph that. So the coordinates are negative 3, 0.5, 3, 4.5, 5, 4.5, 3, 0.5, and back down to negative 3. Sketching these points here, negative 2, negative 3 is on the curve, negative 1.5, I'm just going to kind of eyeball a 0.5 there, 0, 3, 1 and 4.5, so 4.5 again, let's just eyeball that, 2, 5, and you should start seeing, because of the axis of symmetry, which, let me just sketch in here, that looks like the vertex there, there's the axis of symmetry. I don't even need to look at the table of values anymore. I can generate these other dots by just being equidistant, basically the same distance away from the axis of symmetry as the corresponding dots on the other side of the axis of symmetry. So maybe a neat little trick. It's fairly straightforward to graph as long as you can get half of the parabola graphed and the other half comes out as a nice kind of reflection of that. So, second part of the question is determine the x-intercepts of the graph. They don't look like they pass through integer values, and we certainly didn't see that from our table of values. So one technique we can use is for the x-intercepts is to let y equal 0, because we know that the y value has to be 0 at the x-intercepts. And plugging in 0 for y, we get negative 1/2 x squared plus 2x plus 3. And we are going to need to solve this. We could do this using completing the square, or we could go about this using our handy quadratic equation, where a is negative 1/2, b is 2, c is 3, and we would have x equals negative b, so negative of 2, and we go plus or minus the square root of b squared, so that's 2 squared, minus 4ac, so negative 1/2, and c is 3, all over 2 times a. Just some quick simplifying here. Negative 2 plus or minus the square root of 4. Negative 4 times 4 times a negative 1/2 is negative 2. Negative 6 minusing that would be plus 6. and we end up with a -1 on the bottom. So we could change that to technically 2 minus plus 4 plus 6. I guess I could probably write that as 10. So we have an x value of 2 minus root 10 and an x value of 2 plus root 10. So nice exact values. We could dig up the calculator here to show us what those values are, but I don't mind having nice exact values. This is going to end our notes for properties of quadratic functions for Pre-Calculus Math 11.